Assalamualaikum warahmatullahi wabarakatuh. Hi again everyone. Welcome back to the series of videos on pneumatics. We will continue from the previous section on the pneumatic system. Today we will look at the important concept of moisture removal from air. As you are aware, we are looking at pneumatic system. And so because pneumatic system, the basis is using air from the atmosphere, and so we would have the moisture from the saturated air coming into our system. Before, when we look at hydraulic system, we did not encounter this problem because in hydraulic system the medium to transfer energy is oil. So oil is just the amount of oil will remain the same as long as there are no leakage. The oil will continue to be circulated all over our system. But for the case of a pneumatic system, then we would have air coming into our system from the atmosphere, and so we have to worry about the moisture content of the air because the moisture will condensate in our system and it may cause corrosion and will give us other problems. So for this subsection, first of all, we need to know what is some of the important definition includes humidity, where is defined as the amount of moisture in the air, and when air contains the maximum amount of moisture that it can hold at a given temperature, then we can say that the air is to be saturated. There's another term called the relative humidity. This is the ratio of the actual amount of moisture contained in the air to the amount of moisture it will contain if it were saturated. This relative humidity depends on the air temperature. So for example, for air containing a given amount of moisture, if the air temperature goes down, the relative humidity goes up and vice versa. Therefore, there's the term dew point, which is defined as the temperature at which the air is saturated. And thus the relative humidity is 100%. So when air is saturated, means air is at the dew point, any decrease in temperature will cause water to condense out of the air. This condensation process takes place in aftercoolers to remove moisture from the air. And therefore, high pressure air discharged from compressor contains much more moisture per unit volume than does the atmospheric air entering the compressor. The actual amount of moisture per cubic foot in the compressed air depends on the amount of moisture in the entering atmospheric air and the compressor discharge pressure. So we can analyze the relationship between the moisture content of air using this graph. And so from this graph we can see the amount of moisture contained in saturated air at various temperatures and pressure. Okay, so this is the figure that relates the moisture content of saturated air at various temperatures and pressures. And if you look at this figure, you can see the relationship between pressure in the x-axis and the pounds of moisture per 1000 cubic feet of saturated free air at 14.7 pound per each absolute and temperature shown. So for example, if we look at this temperature, say this 80 degrees, it will intersect this y-axis at the pressure of 1.58. So you would, so we look at if we select a particular curve, the intersection of this curve to the y-axis will occur at these values of pounds moisture. So for example, if we choose 80 degrees, the value of moisture at 0 gauge pressure is as shown here, which is 1.58. So if the compressor increases the air pressure of this 1000 cubic feet of saturated free air to 100 pound per square inch gauge, and the temperature is cooled back to 80 degrees, then the maximum amount of moisture this air can hold is reduced to 0.2 pound. So if we are pumping the air from the atmosphere using a compressor, the air originally have 1.58 pounds of moisture at this pressure, but if we manage to maintain the temperature of that particular air, using an aftercooler for example, remember when we pass air through the compressor, normally the temperature will increase. But if we manage to cool it down to maintain the temperature, for example from 80 degrees, maintain it at 80 degrees. So if we increase the pressure for up to say 1, so if we manage to cool it down at the value of 100, then the moisture that remains here is, you can see, it becomes 0.2. So the value of 0.2 means that 1.38 pound out of the original 1.58 pound of moisture per 1000 cubic feet of saturated free air would condense out of the air in the form of water to be drained away by the aftercooler. So this shows that compressing air and then cooling it back to its original temperature is an effective way to remove moisture. So this is an example on how we can calculate the amount of moisture and the amount of temperature that we need to reduce from the air after the compressor if we want to remove a particular amount of moisture from the air. So we can use this chart to help us to determine what kind of aftercooler or air dryer to use. Okay, so we leave the topic of moisture removal and now we go to the next section, which talks about the airflow rate control with orifice. So now we are looking at how we can find the relationship describing the flow rate of air. Remember, in the previous system, for the case of hydraulic, we are using oil as the medium of transfer of energy, so we assume oil to be incompressible. But for the case of air, we are working with a medium that is compressible. Therefore, the relationship describing its flow rate is more complex. So we can this flow rate through orifice can be calculated using these two equations, 13.10 and 13.10, the imperial and metric version of the equations. So Q is the volume flow rate, which is this one. CV, so CV is the flow capacity constant. P1 is the upstream pressure and P2 is a downstream pressure, and T1 is the temperature, which is the upstream temperature. So looking at this equation, the important parameters include the CV, which is the flow capacity constant, which is dependent on the part. So let's look at an example of a manufacturer's explanation on how different CV and how different parts will have different CV and how they calculated the CV.
In this video, we're going to define and illustrate this concept. Valve flow coefficient is a valve's capacity for a liquid or gas to flow through it. It's technically defined as the volume of water at 60 degrees Fahrenheit that will flow through a valve per minute with a pressure drop of 1 psi across the valve. In simpler terms, the larger the opening in a valve, the larger the CV. As a valve is opening, the CV increases until the valve is fully open, where it reaches its highest possible CV, or 100% open CV.
So this is an interesting chart where in the x-axis you can see the percentage of valve opening and the y-axis is the CV. So based on this chart, you can choose what kind of valve that you want.
Here we have a CV chart showing flow curves for two different valves, a 2-inch and a 3-inch Kimray back pressure regulator. As the stem opens, the CV increases. We recommend you select a valve for which the CV falls between 20 and 80% open stem travel. For example, if you used our valve sizing calculator and came up with a CV value of 14, you would want to choose the 2-inch valve because in the 3-inch valve, 14 would fall outside of the recommended range.
So different valve will give different value of CV. So you can use this equation to calculate the flow rate for a given valve, or it may be that you have the flow rate required and the upstream and downstream pressure and the temperature, and you want to select the valve. So you can rearrange the equation to find the CV, and then you can find the valve. The one issue that needs to be mentioned here is that these equations are only valid when P2 here is more than 0.53. P2 is more than 0.53 P1, i.e. when P2 is more than 53% of P1. If P2 is less than 53% of P1, then the flow through the orifice is said to be choked. That means that if the flow is choked, then further reduction of P2 will not increase the volumetric flow rate of the gas. The values of the flow capacity constant CV are determined experimentally as shown in the previous video, i.e. in the manufacturer's video shown just now, and are usually given in table form. The proper size valve can be selected from manufacturer's catalog for a given application. So if you know the system flow rate, the upstream air temperature T1, the maximum acceptable pressure drop across the valve, which is P1 minus P2, and the required pressure downstream of the valve for driving an actuator, then the corresponding flow capacity constant CV, which is this one, can be calculated. So you can select the valve based using this equation, or if you have a valve you want to select the flow rate, you can also use this equation. So bear in mind that CV, the bigger the value, the bigger the valve, the higher the cost. So you have to always evaluate the pros and cons of the valve for your own application. Okay, there's another example, 13.10, which is in the text, which I encourage you to go through. It involves finding the maximum flow rate using this equation. Okay, it's just a straightforward example, so you can just go over it on your own. Okay, next topic will be subsection 13.8. So we can discuss that in the next video. Thank you very much, everyone. Hope you are all safe, in good health. See you again next time. Assalamualaikum warahmatullahi wabarakatuh.